Okay, if we look at example 10, a particle is moving along the curve y equals the square root of x. As the particle passes through the point 16,4, its x-coordinate increases at a rate of 3 centimeters per second. How fast is the distance from the particle to the origin changing at this instant? Now, if you look at the first two sentences of this, it's very much like, I believe it was example 2 or 3 that we did the very first day of this section. They gave us dx over dt, they asked us to find dy over dt, and all was well. And that's what's happening here. They've given us the equation, they've given us a point that the thing's passing to, it's given us dx over dt, but it's not asking how quickly the y-coordinate is changing, it's saying how fast is the distance from the particle to the origin changing at this instant. Okay, we don't have to draw this graph to do this, but I'm going to give you a sketch, just enough to figure out what's going on here. If we're looking at y equals the square root of x, and 16 comma 4 is the point of interest that we're interested in. I'm going to make sure 16 comma 4 is there. Y equals the square root of x, 0, 0, and 1, 1, and 4, 2, and 9, 3, and so on. So it kind of looks like this. That's what that graph looks like. Just a basic sketch is sufficient. You don't have to go to graph paper and get specific points and everything. But the point of interest, the 16 comma 4, is important to us. I'm going to make sure that's identified. And the basic shape of the graph is correct. All right? Now, what I'm being asked here is not how quickly, I'm not asked for dy dx, I'm asked for how fast that's changing. And what I want you to recognize here is points on this graph are in the form of x comma y, right? But officially that's x comma the square root of x. Now, with this intention of when we draw our picture that we don't put numbers where variables belong, all right? Keep in mind the particle is moving along the curve, right? So the curve is set in stone. 16 comma 4 is a point on this curve. The particle is on the curve. So the particle is moving like this, going along the curve. And the curve continues on like whatever. So the particle keeps on moving, right? So x comma the square root of x represents the position of a point at any given moment. 16 comma 4 represents its position at one specific moment in time. The fact that I can go x comma square root of x using this equation is important because that limits me down to one variable to represent a point on the curve, right? What's the other point we're interested in? How fast is the distance from the particle to origin? So the origin. Is the origin moving? No, the origin is where it is. So the origin is 0 comma 0 every time. The particle's moving along, so if the particle's here, that's distance is something. Now the particle's moving in this direction, and you can see that the distance is changing. But hopefully you can tell as I keep going this way, that distance doesn't seem to be changing by as much, right? So as it continues along the curve, it might be slowing down. But x is changing the same speed the whole time. But how long that piece is, we'll see. All right, so this is a changing amount. Where the particle is a changing amount. The variables in play here are going to be x and d. Again, x, y, and d originally, but again, using the equation, we can change it to x square root of x. Now we just have x for the point. We have d for the distance to the origin. Do we have some kind of way to relate the distance from any point x comma the square root of x to the point 0, 0? Is there anything out there in the mathematical world that tells us how to find the distance from a point to a point?
The distance formula? The
distance formula for between two points in the plane, right? And the distance formula tells me the distance between any 2 points of the plane is the square root of the difference in the x's squared plus the difference in the y's squared. And I'm going from x equals x to x equals 0. How far is that? From x to 0.
X.
X. How far is it from the square root of x to 0?
Square root of x.
Square root of x. They're friendly when they give you the origin. They say how fast the distance from the particle to the point, 17 comma 5. They're not as friendly. So anyway, just keep that in mind. But origin 0, 0, x minus 0 is x, and square root of x minus 0 is square root of x. And if I actually work this out, d equals the square root of x squared plus x. That formula relates the distance between the particle and the origin at any given value x that we have, right? So there's our relating equation between the variables we care about. X equals something, d equals something, dx over dt equals something, and dd over dt equals something. What does x equal?
Wow,
16. 16. The point is 16 comma 4, and x is the first number in that. So 16 is x. What is dx over dt?
3.
3, is it positive 3 or negative 3?
Positive.
How do we know it's positive?
If it's increasing.
It says increase, so positive 3, and it's centimeters per second. What does d equal?
I don't know. Well,
We can figure it out, right?
square
Square root
root,
of whatever. 256 plus 2 squared root of 272. We have a relating equation, so if we know x, we can figure out d. We don't actually need to know d, though. When I differentiate, it's going to be 1 dd over dt, then a bunch of x stuff, right? So we are set. We got everything we need in this box in order to differentiate and solve for this thing. The current equation that I have, d equals the square root of x squared plus x, is not in a good form for differentiation, so I would modify that to d equals parentheses x squared plus x to the half power. Same relating equation, but in a better differentiation structure. If I differentiate, again I get 1 dd over dt. I don't feel like I need to write the 1, so I'm not going to. The right-hand side, we do have a product, or I should say a power function, right? We have object to a power, but we have a chain rule also. Remember, when you have to do this dx over dt stuff, and you have to use the chain rule, when you get to the most basic function, that's when you start worrying about the dx over dt's happening. So when I do the 1/2 times x squared plus x to the negative 1/2, just do that as normal. And then when I differentiate the inside piece, which is x squared plus x, that's when I'm going to put the dx over dt's. Square root of x squared is 2x, put a dx over dt on that because x is not t. Derivative of x is 1, multiply that times dx over dt, because again x is not t. 1 times that just makes dx over dt. And just like that, we have a friendly little equation here that's going to tell us what dd over dt equals. All we need to know is values of x and dx over dt, which we know. Again, this was irrelevant. We didn't need to know it, so it's fine. That if we found it, fine. If we didn't find it, fine. I would probably make this a little prettier before I started substituting numbers in. So dd over dt equals, let's see what we can do to make this prettier. X squared plus x, the square root of that goes in the bottom, right? Negative half power. The 2 goes in the bottom with it. And on the top I've got 2x dx over dt plus dx over dt. That's about as pretty as I can make it. And then I just want to put 16 in for all the x's. I'm going to put 3 in for all the dx over dt's. So I'm going to get dd over dt equals 2 times 16 times 3 plus 3 over 2 times the square root of 16 squared plus 16. Again, that's just substitution of 16 and 3 and for x and dx over dt. 2 times 3 is 6 times 16 is 96 plus 3 is 99. And 16 squared, 256 plus 16 is 272. I would probably just go ahead and get a decimal approximation at this point. So if I type my calculator, in fact I got one here on board, choose this one. Clear all this stuff. Alright, so 99 divided by, now what I'm dividing by is 2 times the square root of 272, that's 2 pieces, right? So parentheses 2 square root of 272, in parentheses for the radical, in parentheses for the denominator, we end up with 3.0014 centimeters per second. Had they given us something a little uglier, for example, if it was from the point 2 comma 3, that would be uglier, because now we're going to have x minus 2 squared, square root of x minus 3 squared. Now you got to FOIL all that stuff out, so you're going to get an uglier function in there. It's still the same process. You're just gonna have a little bit more involved stuff here. It's gonna be like 5 or 6 terms in there. So when you differentiate, you have to differentiate 5 or 6 terms here. Okay, but that's how you handle it. So be careful that you pay attention to detail. If it says how fast is the y coordinate changing, that's just like the first example, first day of examples we got. It says how fast is the distance changing from this point. We're going to rely on the distance formula to get us the distance between the points. You want to identify the point on the curve as x comma whatever the function is. Getting everything in terms of x, the distance between the point, and that is what's important.